A plane is flying from New York to London, circling the airport briefly before landing. Sketch a graph of the plane's altitude during the flight and label each section. All right, so if we're flying from New York to London, then circling the airport briefly before landing, we need to think about the altitude at each time. So our x-axis is going to be time, and our y-axis is going to be altitude. Now, assuming our plane is a normal plane, it's going to take off from the airport, and it's going to fly across the ocean. It's going to circle above the airport in London, and then it's going to land back down to the ground. So we're going to have some time where the plane's altitude is increasing, some time where it's maintained, some time where it decreases, probably some more maintained during the circling, and then a decrease again. So when the plane takes off, it's accelerating. It starts by accelerating its speed, but that doesn't change its elevation. So we might see a flat section right along the axis where it's increasing its speed as it goes down the runway, but it hasn't taken off yet. And then we're going to see the altitude increase at a fairly steady rate. Flying across the ocean, it'll maintain its altitude for quite a long time. Then we'll see it start to decrease as it comes into London's airport, but perhaps the airport's too busy and it has to circle for a while. We're not going to see a circle drawn on the graph because when a plane goes into the flight pattern of circling the airport, it maintains an altitude so that it stays out of the way of other planes. And then we're going to see that plane come in and descend. Now, if we were dealing with a situation where it was taking off from Boston, which is basically at sea level, and then landing at an airport in the mountains, it might not come back down to the same altitude, but both London and New York are of similar altitude, so we'll assume that the plane comes back to the same level. Looking ahead to the next problem, it says the graph below shows a trip from home to school and back. The trip involves walking and getting a ride from a neighbor. Label each section. So this problem is similar to the bus ride problem in the what to watch section. So if we know that we are walking and riding, we would expect that we can ride in a car faster than we can walk on our feet. So that would suggest to me that these two intervals are probably walking intervals, because as we notice, their angles are the same, just in opposite directions. And since this graph is defined as distance from home, it makes sense that we should start and stop at the same level. So this is going to be walking to the friend's house. And this side is going to be walking home. Notice there are two flat sections here. If we think about the scenario, we probably either have to wait a bit for our friend to be ready to leave, or we might choose to chat with our friend for a bit before heading home. So these sections are at the neighbor's house. We're not far from home, but we're also not going anywhere. And then we have these two sections in here. They have basically the same angle. They're steeper than when we were walking. So these are the parts that involve getting a ride in the car. So this is the ride to school, and this one is the ride home, or technically the ride to the neighbors. And then we have this long flat section in the middle. Well, typically when we go to school, we stay there for a while. So at this point, we are at school. That flat section represents the fact that our distance from home is not changing. In number 5, it says a graph is shown for a pelican which takes off from shore and eventually dives into the water to catch a fish. We're asked what the vertical scale should show. So that would be our y-axis. So that vertical scale should show the height above the water. And we're asked what the horizontal scale should show, and that should be time, the duration of the pelican's flight. So the vertical scale shows height, and the horizontal scale shows the time. We're asked, why is the section of the graph showing the pelican diving to the water steeper than the section of the graph showing his takeoff? Well, typically, when a pelican takes off, its altitude will increase gradually, but when it dives, it basically just allows gravity to pull it down towards the water. So that fall will happen much more quickly than the takeoff. We want to remember that this horizontal section represents height above the water. It doesn't necessarily represent the path in which the pelican was flying. The pelican could have changed directions many, many times, but if it maintained that altitude, the graph still just looks like a horizontal segment. In number 6, it says, suppose you pour water into each container below at a steady rate. Match each container with the graph that shows the change in the height of the liquid in the container over time and explain your choices. Now you'll notice that none of those graphs looks like the shape of the container. And that's an important key about all of the graphs that we're looking at. We're not graphing the actual path of something as it flies through the air or the actual shape of the mug. We're graphing how something that we can measure is changing with time. So as we look at this, if you imagine filling up the mug, see how the mug has straight sides. So if you imagine filling that up with water, the height of that water inside that mug is going to increase constantly since the diameter of the mug is always the same. If we look at the bowl, the bottom of the bowl is narrower than the top of the bowl. So at first, the height would increase fairly quickly, but then as the bowl gets wider and wider, the water is sort of spreading out as it's filling up. So the water level is going to rise more slowly, even if the same actual amount of water is going in at the same time. So with the bowl, we would expect the height to increase rapidly at first and then to increase more slowly as time goes on. If we look at this like spherical vase, and we assume that the inside is completely hollow, the base is very narrow, as is the top, but in the middle it's very wide. So if we imagine pouring water into this at a constant rate, at the bottom, the height is going to increase quickly, but then in the middle, the height will increase slowly because there's so much more surface area to fill. But then that height level is going to increase rapidly at the end as it gets more narrow. So to me, that's almost the easiest graph to match up because it's the graph that has the most change going on. Whereas the mug from the beginning is the graph that has the least amount of change going on. And the bowl is the one that starts quickly and ends up slowly over time. So the notes here summarize each of the things we discussed. The fact that the mug will fill at a constant rate, and graph 3 shows a line that increases at a constant rate. The bowl will increase quickly at first and then slow down, which is demonstrated by the first graph. And the vase will have a rapid gain in height at both the beginning and the end because of the narrowness of the shape in those sections. But since the middle is so wide, there will be a slower gain in height at that point.